All right, thank you very much for the invitation. I've had a great virtual visit day. So my work comes more on the AGN side, so that'll be evident, I think, during my talk. But I'll be focusing on optical variability from accreting intermediate mass black holes, and hopefully it'll become evident how that's connected with AGNs. So for me, an intermediate mass black hole is around 10 to the 4, 10 to the 5 solar masses. And traditionally, IMBHs are defined between 10 to the 2 and say 10 to the 4, 10 to the 5. Even some people say 10 to the 6 solar masses in terms of the mass of the black hole. So just get that terminology out of the way, and I'll go ahead and get started. So there's 3 things I'd like to cover during this talk if I have time. The first is my work on understanding the optical variability of AGNs, and in particular, the timescale of variability in AGNs, and how this relates to the mass of the black hole. And so after that, I'll discuss the implications for what we think could explain intermediate mass black hole discoveries in dwarf galaxies. And then I'll talk about our work modeling the demographics of these things, and our work trying to identify AGNs with possible intermediate mass black holes candidates for them in the dark energy survey using the deep field fields in the dark energy survey. So first, just to get started with my favorite galaxy, NGC 4395. So one of my first projects as a graduate student was to use TESS light curves to look at AGN variability. So TESS is a small satellite designed to study exoplanets from stars. So you wouldn't think it would be great to study quasar variability, but what's great about TESS is it has a really high cadence and really good quality photometry if the AGN is bright enough. So TESS is a 30-minute cadence, and the typical TESS light curve is, I think, around 1 month long in duration. And so that's a shorter time scale than what we usually study quasars on with typical like SDSS, typical ground-based surveys. So I suggested, well, let's start with NGC 4395. So on the left is a TESS image of the source, and on the right is a ground-based image. So imaging, we're not doing too well, but why study it with TESS? As I mentioned, it's bright, so bright enough for TESS to observe. It's a very well-studied dwarf galaxy that's known to host a black hole mass with a mass of roughly 10 to the 4 to 10 to the 5 solar masses. So all these papers here, and there are more, trying to study the mass of the central black hole of this thing. It's kind of a weird, bulgeless secret galaxy, but it's the sort of poster child dwarf AGN with an IMBH at its center. It's also known to be variable on nightly timescales in the X-rays and optical. But the light curves haven't been studied that well. So I'll skip through all the details of how we extracted the light curves and corrected for the systematic. You can ask me about it in the end. And on the right here is our light curve, which is, we use difference imaging essentially to extract the light curves, and those stars that were shown on the previous slide are comparison stars we use to double check that the photometry doesn't have some systematic residuals in it. But what you see is some stochastic variability, which it turns out is, that's not new. We know AGNs have stochastic variability. So it's not like a supernova light curve where you have a very well-defined sort of behavior. AGN variability is stochastic. And one simple model people use to study the variability is called a damped random walk. So that's the DRW model, which is shown in blue. And so we fit the simplest model that's out there using stochastic Gaussian process time series techniques to try to recover the power spectrum of the AGN, of the variability. And what we found is that the variability can be described quite well by this damped random walk power spectrum, which is essentially a red noise power spectrum that flattens out on certain time scales. So you can think of A random walk is sort of a drunk person stumbling around, and a damped random walk is like a drunk person on a spring, so connected to the lamppost with a spring. So it has this sort of mean reversion to the mean luminosity behavior. So that's what's seen in the damped random walk. And so if you do this sort of modeling, you can do parameter estimation. And we did that, and we extracted a timescale of the variability, which corresponds to where the power spectrum dampens or flattens out. And so what happens is that when you plot that damping timescale on the y-axis versus the black hole mass, we found that its timescale of variability, or the damping timescale, which I'll call tau, sometimes tau damping, in days is about 2 or 3 days, which is well matched to what tests can observe, thankfully. And the black hole mass is 10 to the 4, 10 to the 5 solar masses. And what's exciting is that we found that this lied almost exactly on the relation from quasars from Kelly 2009, if you extrapolate the relation to the intermediate mass black hole, or near the intermediate mass black hole range. But there were some concerns about the quality of these Kelly data, and it's only one data point down there, so you can make an argument one way or the other. So our next step was, can we actually redo this analysis and fill in the gaps on this tau mass relation to prove that there is a relation, or maybe indeed we find that there wasn't. So is there a correlation between the black hole mass and the damping timescale? And does that correlation hold across the full range of supermassive black hole masses? And turns out the answer is yes. So this is our work that I led, which was published last year in Science. And so this is the same figure, same axes as before, optical damping timescale versus black hole mass. And so the black data points here are the optical, and then the red are actually X-ray light curves. So what we're seeing here is that indeed there is a similar trend across the full range of supermassive black hole masses and the variability timescale. And so a more massive supermassive black hole, the longer the variability timescale. So we did this by combining a large sample of light curves. So NGC 4395 is there. We used some dwarf AGNs in the literature, a sample of Seyfert galaxies, and then SDSS quasars to get the full dynamic range of black hole masses to try to build out this relation. In contrast, the slope, the power law, is different when you compare it to the X-ray work that's been done from a previous paper. And so the X-ray variability timescale, we think, traces the innermost stable circular orbit. But the optical variability timescales are much longer, and I was surprised that the slope is actually shallower. It's more like mass to the 1/2 power. So that's not consistent with like an ISCO thing, and it seems that this different slope between the X-ray and optical timescales, different power law, seems to maybe rule out, we think, simple models for X-ray reprocessing driving the optical variability, at least on these timescales that we're measuring. But the question is, how can we interpret the variability? So stick with me here. The way we did this is we assume a Keplerian disk, and we transform the characteristic timescale to a characteristic radius of emission. And so that's what we're plotting on the y-axis now. Instead of timescale is a characteristic radius. So we use this equation here, which comes from the standard thin disk theory. Not all of our results suggest that the standard thin disk theory is correct, but assuming it's some Keplerian disk that follows this radius proportional to the timescale to the 2/3 power, we can make this plot. So we did that. So we know the timescale from our optical data. We know the black hole mass, and we don't know alpha, which is the viscous parameter in the standard model of accretion disks. So what we found is that plotting the same data, this time for radius, and assuming fixing the value of alpha to 5%, we found that our trend, our correlation, matches the constraints from Morgan 2018, which are observations of microlensing observations used to derive accretion, AGN accretion disk radii. So the microlensing constraints are shown in blue, and our correlation, assuming alpha of 0.5, is shown in the data points there, and with the best fit power law model. So we think this is consistent with the picture where the optical variability is driven by at the UV radius of emission with a viscous parameter of around 5%, but there's some degeneracy there. And so, but we think we can rule out the dynamical time and other time scales, certainly like the viscous time and standard accretion disk theory. So that's quite exciting. And the other thing I'll point out is that our relation can probe the entire range of supermassive black holes from 10 to the 4 to 10 to the 9 or so solar masses, whereas the microlensing results are limited to quasars, which have a smaller dynamic range and mass. But we thought, well, why stop there with AGNs? And what happens when you look at stellar mass accretion disks? So we, one of our co-authors, Scaringi, has really great power spectra of a sample of white dwarfs, accreting white dwarfs, nova-like white dwarfs. And we plotted their damping timescales measured in the optical, correcting for the wave rest frame differences. And what we find is that it is within 2 sigma consistent with an extrapolation of our timescale mass relation, which we then can easily be explained by some sample selection effects. And so, this is controversial, but I think it's potentially interesting. And if it has any merit, then it means that in between here, of course, is the missing gap between stellar mass accretion disk and supermassive black hole accretion disks, and that's the intermediate mass black hole range. And what's interesting is the damping timescale, or the characteristic variability timescale of an intermediate mass black hole, if it follows this relation, should be hours to days, depending on the exact mass of the IMBH. So that could partly explain why these things have been kind of difficult to find before, right? If you're just using ground-based photometry. Okay, so by the way, feel free to interrupt with questions. If there are none at this point, I think I'll move to the second part of my talk, which is we're trying to build a forward model for AGN variability. I think there's one question. Matthew?
Yeah, sorry, Colin. Just on the your alpha relationship, you're saying you're assuming a thin disk model, but the microlensing results tend to suggest that the radius of the thin disk model is wrong, doesn't it? Microlensing tends to suggest it's larger. So I'm wondering if is there an inconsistency there?
Yeah, great question.
Both are holding or not?
We don't think there's any inconsistency with this picture because we think if those, indeed, the microlensing radii are not consistent with the standard model, but as long as you still have a Keplerian disk with this, radius proportionality with the mass and the time scale, then, you can still have a fudge factor there to get larger radii. So, okay. Yeah, it is a more complicated picture than just the standard disk theory, but we think the scaling of our timescales roughly does match the standard than disk theory.
Yeah, I mean, what I will say is that I think this, this agrees with what we found with these changing state quasars, where the timescales were, we believe that those effects are propagating through on the thermal timescale, and I think alpha is. Not that we can constrain it particularly well, but it's in the sort of range that you're finding there as well.
Yeah, great. That's very exciting. We think this alpha value is reasonable, but people have different ideas. What's driving the variability, I should say, is we have this nice picture where we're plotting the thermal time, but the local thermal time in the disk, what drives that variability is completely unknown. So we're not saying anything about that as well.
No, I agree entirely.
Great. Other questions? Okay, in that case, I'll move on to the second part. So so now that we think we're getting at how these IMBH dwarf AGNs, how their variability might behave, I'll try to motivate why we're interested in actually forward modeling this variability and what we can learn from it. So this is a picture from a review by Ms. Kua, 2017, which shows different scenarios for how supermassive black hole seeding works. And so on the y-axis is redshift and the x-axis is black hole mass. And the basic picture is that we think that in order for supermassive black holes to have formed and come to occupy nearly every massive galaxy in the local universe, they need to have been grown by accretion and mergers, but they need to have been seeded probably at higher redshifts by a smaller black hole, an intermediate mass black hole. And so there are all kinds of different ideas for how you can get intermediate mass black hole things to form at higher redshifts, these seed black holes, like direct collapse of gas clouds in the early universe or population 3 stellar remnants. And then, those things can evolve across cosmic time. There's people here who are thinking about this, who are experts, and I'm not one of them. But the basic picture is that some of these IMBH seeds could be left over, which for whatever reason haven't grown and accreted over time. And we might be able to observe these in the local universe through the fraction of dwarf galaxies that have low mass AGNs. So in other words, the fraction of dwarf galaxies traces the black hole mass function in the local universe. And this could help basically by counting the number of IMBHs candidates that we can observe using in dwarf galaxies. We can potentially constrain the black hole mass function in the IMBH regime, or start to get down at it from the AGN. Again, I'm coming from the AGN side and pushing down. So that's one motivation, trying to understand seeding, trying to constrain theoretical models for seeding and growth over cosmic time. And that fingerprint could be something we can observe. This is another slide, I'll just go through it quickly, motivating some of this work. So these are not AGNs per se, but these are some of the best candidates for intermediate mass black holes that we know to exist. Well, they're controversial, some of them. So the first one here is a hyperluminous X-ray source, which is like an ultraluminous X-ray source, but hyperluminous because its X-ray luminosity is roughly 10 to the 39 ergs per second. And this is, I think, it's been studied, its X-ray spectrum and X-ray variability is quite weird. And there's a group that argues that this is an intermediate mass black hole. Again, don't ask me the exact details. And again, it's controversial. But if they're right, it has a black hole mass of 10 to the 4 solar masses, which would put it in the IMBH, upper side of the IMBH regime. And what's interesting is that it's actually not in the nucleus of the galaxy. So calling this active galactic nucleus would be wrong. It's off nuclear. And so sometimes in the AGN community, we would refer to this as a wandering black hole, wandering in the outskirts of the galaxy. And so this one, I think, they think could be a tidally stripped dwarf galaxy or something like that, but it's not in the nucleus. A similar one is shown on the bottom, which has this XMM telephone number. This is actually a TDE, and these authors argue that the behavior of the TDE is consistent with a similar mass of an IMBH, TDE around an IMBH. So TDEs are a really exciting way to find IMBHs, because in order to get a star to tidally disrupt, you need a lower mass black hole. But again, this is not in the nucleus of at least this large galaxy. It's kind of out on its own. And then the third one I'll put on here is the LIGO Virgo event, DW 190521, which had a remnant mass of like a little over 100 solar masses. So by the technical definition that we all use, 100 solar masses or more that is a IMBH. So just to motivate some of the, what we know, some of the best candidates for IMBHs, true IMBHs that are out there. We can also find things, as I've been talking about, from the AGN side. So this is work by Vivian Baldassare, who identified optically variable galaxies, which have, that should be stellar mass, not black hole mass. So she identified optically variable galaxies with a stellar mass of less than 10 to the 10 solar masses using the SDSS catalog. And I think she used PTF photometry and looked for things with variability. And so this was restricted to the SDSS catalog with galaxy properties, stellar masses. And if you see, like on the bottom right here, something that looks quite convincingly like an AGN in a dwarf galaxy with a 10 to the 7, 10 to the 8 stellar mass galaxy, then that's, I would say, an interesting candidate for an IMBH, something on the upper end of the IMBH. It's hard to fit a supermassive black hole in a galaxy that small. And we know there's, so I'll leave it at there. And so this is the variable fraction that they found versus, so the fraction of galaxies that show significant variability versus the stellar mass of the host galaxy. And it's interesting that the fraction of dwarf galaxies below 10 to the 9 solar masses isn't 0. It seems to be non-zero. And so I'll get to, but it's hard to say anything more about that, about the black hole mass function, for instance, because it depends on the level of variability that you can see. So to try to disentangle this, we're building a forward model for AGN variability. So how do we do this? Well, you have to do it in a way that's self-consistent with the host galaxy information. So we're starting from the starting point, which is the galaxy stellar mass function. So this is the galaxy stellar mass function from gamma observations, and I think also constrained using cosmos imaging. So these are the best constraints in the literature. And I'm plotting the gamma data here in red. There's some incompleteness below 10 to the 7 solar masses from surface brightness, but it's not a wild extrapolation to get to 10 to the 6 solar mass dwarf galaxies. And one interesting note is I also plotted like the quick and dirty SDSS galaxy stellar mass function. And you can see, it's limited by the SDSS spectroscopic. This is a spectroscopic catalog, which has black hole masses and properties, which has been used to do all the previous observational studies. And this is missing most of the dwarf galaxies that are out there because the spectroscopic targeting is quite shallow. It's like R mag 17.8. So that's an interesting thing that, well, it's these studies that the current observational studies are highly incomplete. So take that as a caveat. After that, you can pick whatever model you want for the occupation fraction. So this is the fraction of galaxies that have a supermassive black hole or a massive black hole in their near their center that's associated with the stellar mass of the galaxy. So we know that's roughly unity for massive galaxies, but take your pick at which seeding scenario you want, which simulation work you've picked. It's unconstrained right now in the dwarf galaxy regime. So we picked two scenarios. The blue one you can think of as a light seeding scenario where you have a lot of IMBHs, and every galaxy has an IMBH. Every dwarf galaxy has an IMBH. And the magenta here is a more pessimistic occupation fraction where like seeds were quite heavy seed formation. And so there aren't many IMBHs. And so really dwarf galaxies, the fraction of dwarf galaxies with an IMBH goes to 0. So you get this sort of S curve. So that's a pessimistic scenario, just to bracket the possibilities. After that, we know that the mass of the host galaxy is connected to the mass of the black hole. So we use the black hole mass stellar mass relation. to go from stellar masses to black hole masses. And when you do that, you get the black hole mass function. And so we're showing the two different black hole mass functions for the optimistic occupation fraction in blue and the pessimistic one in magenta. And then I've added an even more optimistic thing, black hole mass function, that's tied to gravitational wave LIGO Virgo merger rates constraints from gravitational wave observations. So this is a model from Cecilia 22, which did a forward model using stellar evolution codes and binary and single stellar channel evolution, and they can seemingly reproduce them LIGO rates. And so there are some constraints in the lower end to try to anchor the black hole mass function at 10 to the 2 solar masses. But I've gone and done something kind of crazy and assumed that there's a smooth power law, because astronomers like power laws, between that's consistent with those LIGO Virgo rates and consistent with the galaxy stellar mass function in the supermassive black hole range. So I've assumed that green is a smooth power law. After that, you need to pick a Eddington ratio distribution function for the sources, which I've gotten from a previous work, and that's probably the most uncertain thing in this work. It's not well constrained in the dwarf galaxy range, but we think it depends on the host galaxy type. So anyway, you can ask me about it later, but that comes from observational constraints. So this is all empirically motivated to the best extent, as best as we could. After that, you can finally get the bolometric luminosity function and for local AGNs. And you can extrapolate that to the IMBH range, so the really low luminosity AGNs that might have IMBHs. And so we've got the pessimistic scenario, the more optimistic and blue, which says that every dwarf galaxy has a black hole there. And then the green is the even more optimistic one, tied to LIGO rates, which assumes that a galaxy might have tens or thousands of IMBHs in them, but not necessarily associated with the nucleus of that galaxy. Those could be the wandering population of black holes. And so what we found is that this is still consistent with the luminosity function that is constrained for AGNs. And so that's the red crosses and the red power law thing there on the right at high luminosities. And so one's from optical and one's from X-ray, and then you assume some bolometric correction. But this is not constrained below like 10 to the 42 ergs per second. So beyond that, you're free to pick whatever extrapolation you want that's consistent with your population of accreting IMBHs. But to try to root things a little bit further to make sure we're not crazy, I've also plotted let me go to the next slide. I think I blew it up here. I've also plotted the luminosity function of in the filled squares of ULXs, ultraluminous X-ray sources, which some may be IMBHs, and some may be smaller things like neutron stars or stellar mass black holes that are super Eddington accreting. But at least we can say that, okay, our predicted IMBH luminosity function doesn't wildly exceed the luminosity function for ULXs. And so if that were the case, then IMBHs, we probably would have found plenty of them by now. And so this is the most optimistic scenario. And so, and then in the open squares there, I've done the same thing for X-ray binaries luminosity function in globular clusters. And so I'm not saying anything about how IMBH variability accretion is in any way like ULX or X-ray binary accretion, just to say that, okay, our predicted luminosity function doesn't wildly exceed the luminosity functions of those sources. So after we've done that, I have included a simple model for AGN optical variability. And so this has been studied before by previous papers using the SDSS data set, and Matthew Graham has worked on this as well. I'm sure that we have many thoughts. So I think we figured out the variability timescale. So in the damped random walk model, we have a timescale for the variability, and we also have an amplitude. And so I've used the timescale mass relation in the IMBH range to predict the light curves in terms of the timescale. But what's the amplitude of variability? And to do that, first I extrapolated the SDSS relations, which are shown in gray for different Eddington ratios. And when you extrapolate that, SF infinity is like the RMS of the variability, so change in magnitude. And when you extrapolate those to the IMBH regime, you get some wild answer, like over 1 magnitude of variation in the optical band, which would be crazy because IMBHs would be too easy to detect. We would have found them by now, most likely. So we just did some simplest thing I could think of is to dilute the variability. So these SDSS quasars are all bright quasars. They have, we're assuming, essentially 0 negligible contamination from the emission from the host galaxy starlight. But that's not true when you get to lower stellar mass galaxies. So there, the AGN emission, the star forming emission starts to swamp out the AGN emission, and the variability amplitude is suppressed. And so that's that simple host galaxy contamination or dilution correction is shown in blue here. And the uncertainty on that is pretty big. And so to get the luminosity of the host galaxies, we have to use mass to light ratios. And then this is all tied in again to the stellar mass, black hole mass correlation as well. So the luminosity of the AGN in our model, we're also taking from color temperature corrected models of theoretical models for the SED from Dunn 2012. And so on the bottom here are 2 mock light curves, one with a 10 to the 6 solar mass black hole, supermassive black hole on the lower side, and then an IMBH of 100 solar masses. And you can see that the time scale is much shorter, and the optical variability amplitude is less, around 1/10 of a magnitude or less. So this is really challenging to observe with current facilities. But the scatter in the relation is large. So if you get lucky, you're probing the scatter and the variability amplitude at low masses. This is a similar plot, except I've showing the variation in the covering factor, which is how much of the host galaxy luminosity is included in your photometric aperture. And so when your galaxy is unresolved, it's a small dwarf galaxy that starts to go to unity. But for a Seyfert galaxy that's well resolved, like NGC 4395, which is this data point here, it's got much lower covering factor. So not all of the host starlight is being diluted from the nuclear region where the variability is coming from. So this is a simple phenomenological model. And you can run that through a code that simulates the cadence and photometric precision for whatever survey you're interested in. So we have a Python code to do this. And I've compared this to the current observational constraints, which are from the PTF survey, matched to SDSS galaxies. So that's shown in red here. I still showed that on the previous slide. This time it's a log scale. So this is the variable, the fraction of galaxies that are variable as a function of log stellar mass. And what we see is that our model, using the 2 different optimistic and pessimistic scenarios, produces roughly the right variable fraction of galaxies. But the current observational constraints don't have enough statistical power to really rule out one or the other, to say which occupation fraction or galaxy stellar mass function is appropriate. There's some and it also reproduces the rough shape that you would expect as a function of galaxy magnitude, which is shown on the right-hand side. There's some inconsistency here, which could be due to incompleteness in the observations or something wrong with our model. But the ultimate hope is that can we use this model to constrain the occupation fraction or the black hole mass function in the dwarf galaxy regime with future surveys like Rubin Observatory. And so we're currently working through another set of simulations with Rubin Observatory like parameters to try to predict what the prospects are for doing this with Rubin. But again, the caveat here is that how well or not the local occupation fraction actually traces these seeding mechanisms is certainly an open question for theorists. And so hopefully eventually we'll have a nice data point, nice constraints on the black hole mass function at lower masses for theorists to use for their seeding models of black hole growth. We can do a little bit more since we have a forward model of aging and variability. And so this is plotting the black hole mass versus host galaxy stellar mass that we can recover from variable sources. And as shown in gray is the input host mass, black hole mass scaling relation from Rhines 2015, I think it is. And in the magenta and blue is the recovered variable population that we're recovering. And there's a selection bias here. So this makes it even more difficult. So at lower stellar masses, you're actually probing higher black hole masses than you would expect based on this relation, just because those tend to have less dilution from the host galaxy luminosity. And so there's a bias in the recovered relation here. So this, I think, shows the importance of getting alternate ways to measure the masses of black holes in these dwarf galaxies, because they may not fall on the stellar mass, black hole mass relation exactly due to selection effects. So one way to measure these masses is using our variability timescale mass relation. Another way is broad emission line techniques. Those are difficult. You need high signal to noise spectra, et cetera. So what we did is we tried to say, okay, well, if we have an optical survey, what are the prospects for actually getting their black hole masses from the timescale of variability? And so this is some preliminary work we've done using different cadences with like a Rubin-like depth. And so on the y-axis here is the recovered black hole mass using parameter inference from the variability timescale. So, and on the x-axis is the input black hole mass of our simulation. So these are idealized simulations of damped random walks, but it probably gives you an idea for what the effect of the cadence is and on doing this type of analysis. And not surprisingly, what you find is that below a certain cadence, you lose those timescales. And so if your cadence is 25 days, it's hard to measure the black hole mass using the variability timescale below like 10 to the 6 solar masses. Because essentially your light curve is not sampled at a high enough cadence to sample the full frequency of the power spectrum, to be able to constrain a break in the power spectrum, essentially. And so when you do this with a ZTF-like cadence of 3 days, it's actually much better. You can get close to the IMBH range into the 4. So 3 days corresponds to like NGC 4395, barely like a 10 to the 4, 10 to the 5 solar mass black hole. But below that, it's hard to get a black hole mass from the variability. And so what's shown on the very right-hand side is what happens if we use a hybrid cadence with a 30-day light cadence, which you might have with LSST, wide fast deep, wide field survey. But then we supplement it with a 2-hour cadence where we hit this field for 5 nights or a week, if you can. And we find out we can, in fact, recover IMBH masses using those timescales because you have a wider sampling of timescales in your light curve. So you don't need to have a uniform sampling of times as long as you have some hourly cadence observations. There's, I think, a hope to study these light curves of an IMBH if they're out there. If you want to learn more, you can read a white paper by Eric Bellum and I and others. And we make the case for other science cases to use for a high cadence supplementary survey. So I think it's an interesting direction. Finally, I don't have much time, but I'll go very quickly. We're doing some work with the dark energy survey to identify low mass AGN. So this is similar to Vivian Baldessare's work. We're just selecting from optical variability using stellar mass catalog. In this case, we used our own stellar masses from the dark energy survey. And so the example light curve is shown here on the top right. And so this is a few square degree field. So it's not a wide field thing like Vivian's paper. It's a few square degrees, but it's deeper. And we have really great light curves in these fields. So this is an example of a source we identified in our paper, which is on the archive. And its variability timescale is around 1 month, which is consistent with the spectrum, which we happen to have a spectrum from SDSS. And it's quite noisy because it's a small black hole mass. It's at a higher redshift of 0.8. But its virial mass is consistent with what you would expect given the timescale relation, even though this thing is at lower masses and higher redshifts than in a parameter space that's been difficult to probe currently. So that's, I think, a nice demonstration. It's not an IMBH, but I think it's a nice demonstration of using deeper surveys to do the same work. And so this has a stellar mass of like 10 to the 9 or so solar masses using the SED. We did some SED fitting. I would take the SED fitting with a grain of salt because it's notoriously tricky when you have an AGN in there, and we only have UV and optical IR data for everything. So, but the variability timescale, I think, gives you a nice reassurance that this is on the lower end of supermassive black holes. Again, I said take the SED fitting with a grain of salt, but here's the rough stellar masses versus photometric redshift for our sources in these dark energy survey deep fields. And our AGNs are shown in red here. And the ones with rapid variability, which is around a month or less, where the DS light curves are more sensitive to, are shown with the red crosses, red stars. And what we see is that this indeed probes higher redshifts and lower, given a fixed redshift, it probes lower stellar masses systems. And so for comparison, here's the Vivian Baldessare wide field survey work and similar work using ZTF data from Ward 21. Okay, and I think I'm at 45 minutes, so I'll just thank you for your attention, and I'll summarize by saying I think optical variability is an interesting new way to identify IMBHs coming from the AGN side of things. And it also gives you interesting insights into AGN variability in a smaller different mass range, different parameter space. But to get black hole masses using this empirical variability correlation does require really high quality, high cadence light curves. And so for an IMBH, you need that high cadence to attempt to really put this to use. And so I talked about our work developing a forward model to try to constrain the occupation fraction in the local universe and our possibility of extending beyond the local universe using dark energy survey data. So I think it's an interesting time, and hopefully we can say something more with future observations in the near future. So thanks for your attention. I'll take any questions.
Thank you, Colin. That was really interesting. Okay, just raise your hand if you got a question. We can call on you from the participants list. Yeah, I can start. So we kind of touched on this a little bit when we were chatting earlier today. But when you showed the black hole mass function, you had those three curves, green, blue, magenta. I think green was the super optimistic one. I think if there are 100 or 10, like 10 to the 3 solar mass black holes per cubic megaparsec, those will show up in gravitational lensing, like time delay gravitational lensing for things like fast radio bursts. Maybe not GRBs, maybe there's not enough of them. So I guess my question is, like, how seriously do you and do others in the field actually take a curve like that?
Oh, I think this is highly optimistic. I wouldn't put my money on it. So yeah, that's an issue. I hadn't thought about using those constraints to limit this. So I think if there's a way we can rule out some of this parameter space using those observations, we should definitely do it. So yeah, I mean, this is super optimistic. You know, we have found some wandering black holes candidates, IMBHs, and there's some observational studies that have found these things, but they're controversial. So yeah, I would say I would take it with a grain of salt. I'm just trying to show that there's different possibilities that could be reasonable and what effect that would have on the observations.
Okay, so if those wandering black hole candidates were real, where would they fall on that green curve?
Well,
Rate of detecting one or a few?
yeah, it depends on their number density. I don't know if, like if you take the, I know there was a sample of wandering black holes identified in the radio, and it's a good idea. I don't know if you can get a like quick, you know, number density from those observations with big uncertainties. But if you take those as being IMBHs, which they may not be, then that might be an interesting thing to double check the consistency with. Yeah.
Interesting.
Mm-hmm.
Okay, are there other questions? I have another sort of trivial question, which is in the first couple of slides when you were talking about estimating the power spectrum from the random walk.
Yeah.
Are the results actually that different from just taking a power spectrum of the data itself?
Yeah, I kind of skipped over the technical details of that. So in our paper, we did show just the Loam-Scargill power spectrum directly computed from the data. And in this case, it's possible to do it because the light curve is really well sampled. But it turns out for most light curves that you have from the ground, you know, you have gaps from weather and nightly day-night cycle, and they're very sparsely sampled and unevenly sampled. And even when you use like the known power spectra methods like Loam-Scargill, it's still hard to reconstruct the true power spectrum using that. So we kind of get around this by assuming a statistical model that can describe the light curve in the time domain, and then backing out the power spectrum of that model. Yeah. And so you have to do this in a very statistically motivated way, and it's a little bit of a dark art sometimes, but yeah.
Fair enough. Okay, I think Matthew has a question.
Yeah, so there's this idea that IMBHs have hotter accretion disks.
Yeah.
And so that gives you a sort of harder broadband continuum, I think, compared to sort of the more massive systems. Right? I'm wondering whether that means that you might expect to see a slightly different variability characteristic, particularly if you're sort of trying to connect the SCDM with the variability, and whether that has any effect then on what you're seeing or what you're interpreting in that particular case.
Yeah, certainly. So if I understand the question correctly, and maybe I'll talk about this slide. So this is on the left here are our STD models we've used. And so this Doan 2012 thing has this color temperature correction where at lower masses, indeed the temperature changes and SED shifts into the UV, extreme UV. So we did include that, and then we assume that these variability, observed empirical variability relations still hold depending on for that AGN luminosity that you get from this SED.
Oh, okay.
Yeah, so that's the best we could do.
No. Okay, yeah. I mean that makes sense. So you're at least, I mean, you're at least sort of trying to account for it to some extent.
Right.
So, yeah. Okay.
Any more questions? Okay, if not, well, thank you very much again, Colin. That was a really cool talk.
Yep, thanks for having me.
Yeah. Just end the recording. And at some point, this this recording will end up on YouTube.